Welcome to the AI Research Roundup. I'm Alex, and today we're looking at a paper from the Hugging Face trending list, published just a week ago, which introduces a new method that's an incredible 2 times faster than standard diffusion models. The paper is titled Marrying Autoregressive Transformer and Diffusion with Multi-Reference Autoregression. Alright, so this paper introduces a model called TransDiff, which combines autoregressive transformers with diffusion models. An autoregressive model, well, it generates content step by step, where each new piece depends on the previous ones. Here, the transformer creates high-level semantic features, basically the core meaning of an image, not just its pixels. These features then guide a diffusion model to create the final picture. Building on that, the authors also introduce Multi-Reference Autoregression, where the model looks at several previous images to generate the next one, and as we'll see, the results are very impressive. Also, the authors shared their official PyTorch implementation on GitHub. In the repo, you'll find everything you need to get started, including pre-trained ImageNet models, a demo notebook to play with, and of course, the full scripts for training and evaluation. It's all there for you to explore. And over on Hugging Face, you can grab their pre-trained models from 290 million up to 1.3 billion parameters and try them out with the provided notebook. Alright, so to really understand the core innovation here, this figure compares different autoregressive strategies. On the left, you have traditional methods. Token-level autoregression builds an image patch by patch like a puzzle. Scale-level autoregression starts with a blurry, low-resolution version and progressively sharpens it. But the new method, multi-reference autoregression, is fundamentally different. It generates a new, complete image by referencing several other complete and diverse images. This approach of using multiple full references helps the model learn richer patterns, which is a key reason it achieves such high quality. Building on that idea, this diagram really clarifies their TransDiff approach. It contrasts traditional methods, like autoregressive models using discrete tokens, or very slow diffusion models with their new hybrid system. The key here is that the autoregressive transformer doesn't create pixels, but rather a continuous high-level feature, basically the core idea of the image. This feature then guides a much faster diffusion process. The diagram also shows their multi-reference autoregression in action, using several complete images as context to generate the next one, which dramatically improves quality. Moving to the results, this table really puts those claims to the test. It compares TransDiff against other models on the ImageNet 256 by 256 benchmark. The key metrics are Fréchet inception distance, or FID, where lower scores mean more realistic images, and inception score, or IS, where higher is better, and the results are stark. The TransDiff model using multi-reference autoregression achieves a state-of-the-art FID of 1.42. But the incredible part is the speed. It takes just 0.8 seconds, while a leading diffusion model like DIT-XL2 takes 45 seconds. This table then digs deeper into why multi-reference autoregression works so well. It compares the standard one-step autoregression, the older scale-level autoregression, and the new multi-reference autoregression. The key column here is measure. This represents the diversity of the high-level features, where a lower score is better. As you can see, multi-reference autoregression achieves the lowest diversity score, which then translates directly to the best Fréchet inception distance of 1.49. This result really supports the idea that referencing multiple images helps the model generate richer ideas, leading to higher quality pictures. And now, to see what those numbers actually look like, this figure gives us a direct visual comparison. On the left, you have images from a model called VARD24. In the middle, another called MRAR-H. And on the right, the new TransDiff-H using multi-reference autoregression. The quality improvement is really clear. The TransDiff images of eagles, cheetahs, and people in hats are sharper and more coherent. This visual evidence perfectly matches the Fréchet inception distance scores we saw, with TransDiff achieving the best score of 1.42, confirming its state-of-the-art performance. So what's the big picture here? Well, this work on TransDiff shows that by cleverly combining an autoregressive transformer with a diffusion model, we can get the best of both worlds. The model generates images with state-of-the-art quality, while being over 100 times faster than leading diffusion methods. The key innovation is multi-reference autoregression, which looks at several complete images to create the next one. This approach opens up some really exciting possibilities for fast, high-quality image, and even video generation. That's all for this week's Roundup. Thanks for tuning in.